Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is the AAS Journal Author Series. And I am super happy to have Frederick Gent with us today. Hey, Fred.
Hi, thanks for having me. Very pleased to be here.
Well, thank you so much for talking about your very lovely article. It's a beautiful one. Very nice. Very nice. And Fred, where are you located at?
I'm in Espoo in Finland at the University of Aalto,
Very
Computer
cool.
Science Department, and working with Marit I should change the name, Marit Korpilag, who's my PI and in charge of the astroinformatics.
Very cool. Very cool. Let's see, it is June 28th of 2023, so we're in summer, and so the days must be very long there in Finland these days.
It's very nice.
It's one of my bit buckets and things in life to do is to make it up to the northern altitudes and actually see the northern lights at some point in my life. So maybe
I'd quite like to see them as well every time I go. It's cloudy or raining.
So maybe I'll make it up to Finland one day and watch it out. So very cool. Very cool. So I am in Phoenix, Arizona, and we're a little bit different than Finland, and we have definitely hit the power switch, and we are definitely warm in the summer. Very cool. Good. And Frederick, what do you like to do for research?
Well, I mainly study the dynamo and the interstellar medium with respect to both small-scale and large-scale dynamos in galaxies. I spend most of my day trying to simulate galaxies, and when it doesn't work, spending most of the rest of the day trying to fix those simulations to get them to run. And working with a group that are doing high-performance computing. So the simulations that currently doing, the longest one of those has been running more than 2 years.
Wow.
Doing the same simulation. It hasn't been running continuously for 2 years.
Yeah, okay, sure.
I looked at its earliest snapshot, and it turned out it had been started more than 2 years ago. So, and the simulations that I'll be talking about typically took a few months each to run. At least some of the largest ones took a few months.
Wow, that's impressive. Very cool. Very cool. And that is going to bring us to this very awesome APJ article. It is open access. It's the open access era, people. You can go grab a copy for free. Go get one. The small scale dynamo in multiphase supernova-driven medium. And Fred, take us away.
Right, thank you. So this paper on the small scale dynamo in supernova-driven turbulence, I've written with Mordecai Mark Macklow, who is at the American Museum of Natural History in New York, and who's probably familiar to many people who are regulars to the Astrophysical Journal.
Indeed.
Great significant expertise in interstellar medium simulations in general, and the physics of molecular clouds, star formation, that sort of thing. And we've also written it with Marit, who I mentioned earlier. Yep. Her expertise is quite extensive in all aspects of dynamo and dynamo theory and numerical modeling, particularly more so with stellar dynamo, but she actually did a PhD in supernova-driven turbulence. Cool. Something which I very much followed on from with the work I've been doing. And then she's also at Aalto University. And then Nishant, who was working with Marit for some time at MPS in Göttingen. Oh, yeah. That's the Max Planck Institute for Solar Physics Research. That's not exactly the right translation, but it's something like that. And he's now at Ayuka in Pune in India. And his expertise is, again, very much theoretical understanding of dynamos, particularly the nature of small-scale turbulence in dynamos.
Very nice. Great shout out. Very good.
And the motivation for doing this particular paper was to understand the small-scale dynamo in the interstellar medium, which has been studied theoretically and with very kind of simple models that have similarities to do with the interstellar medium and the nature of the physics that are there. But not quite so realistic in terms of the presence of supernova or the multiphase structure that we are trying to capture.
Yes.
A lot of the previous work I did in this area included the large-scale dynamo. So it was a galaxy which had rotation, was stratified. And in this case, we want to try and understand what the difference is, or at least what the nature of the small-scale dynamo is, how effective it is. We had some discussion in the background with people we've worked with at Potsdam, AIP in Potsdam, where there was some debate as to whether or not there is a small-scale dynamo present.
Fair enough.
Based on earlier experiments, which we actually refer to, I think it might have been in the earlier paper actually by Balzer et al., where they did some simulations, virtually the same setup as this, but with an older code, with more diffusive code, and they clearly, in my view, produced a small-scale dynamo.
Okay.
And then our collaborators at Potsdam attempted to do similar sort of simulations and failed to find a dynamo. So that's what cast some question of this. We did a few early experiments. It was quite clear that there definitely is. Very easy to excite a small-scale dynamo. Now, when I say small-scale dynamo, I'm talking about a dynamo in which the magnetic field grows on the length scales of the turbulence, or similar to the turbulence of the flow. So it doesn't have any large-scale structure.
Right.
And in order to do that, we produce these models which have no stratification, no rotation, no large-scale effects at all, and we just inject into a uniform medium multiple supernova over a period of time and to build up the turbulence and to see how the dynamo grows.
Got it. Okay, cool.
We find if you move to the first image, a little bit further down.
Large scale dynamos, figure one.
We did multiple models, and within those models, we looked at different resolution for models that otherwise had very similar physical statistics or physical parameters. Yeah. And so shown in this top panel, in fact, both panels show the same thing, just the difference is the scale on the bottom panel is linear, the time scale, whereas it's logarithmic on the top panel. And that's just to try and show a little bit more detail for the high resolution runs, which are incredibly fast compared to the lower resolution runs. Mm-hmm. And you can see that for the model in blue and green, with a resolution of 0.5 parsec and 1 parsec, that these actually, I would argue, are convergence. That we produce a dynamo which grows very rapidly within tens of mega years, and has roughly the same growth rate, and then saturates at roughly the same magnitude. Mm-hmm. This is relative to the kinetic energy density of the system. With slightly, with somewhat lower resolution, the 2 parsec resolution, 4 parsec resolution, that's the red and the dotted lines, you see that we don't actually have a dynamo that actually, with the same parameters, it's because of the lower resolution, the system is numerically more diffusive. We don't capture the small scales as well, and it fails to produce the dynamo. There is, however, for the 2 parsec resolution, around about 100 mega years.
Right about here? Mm-hmm. It's trying.
So there is actually something which drives the dynamo for this one. And when we looked at models with different parameters, these were the higher resistivity. So it was less likely to produce a dynamo, but it still did so for the higher resolution models. Okay. When we look at slightly less diffusive models in the low resolution, they also produce a dynamo, but much more slowly. And clearly not converged with, in fact, we get a false convergence here compared to the high resolution run.
Yeah, fair enough.
And you can see the differences in the growth rates in the lower panel, which have been fitted. And although there's slight differences, the growth rates are clearly very similar at 1.5 parsec resolution. So our argument is that at 1 parsec, these models are numerically converged, or approaching convergence anyway.
Right, just to set a sense of scale here, this dotted black line is...
So that dotted line shows, well, actually it shows 2% of equipartition. So this is, I'm pleased you asked that question. So normally when you have a dynamo, and certainly from the theory and a lot of isothermal simulations where the turbulence is much simpler than this, and particularly if the Mach numbers are lower, what will tend to happen is the dynamo will grow very fast and exponentially, which is happening in the later stages of the blue and the green line there. But they're saturated around about equipartition with the kinetic energy.
Got it.
Actually, no, I'm wrong about that black line. It is actually equipartition, because what we found is that the equipartition is around about 2 to 5%.
Okay.
And that's where you see that it's around about 10 to minus 2 on the scale. So it saturates lower. Now, this is quite consistent with a lot of people that looked at simpler models with high compressibility.
Great.
What was kind of extra confusing to us and of interest in this paper is the fact that the growth isn't a simple exponential growth, which is often what's seen with these dynamo models. It's just the whole system grows at one scale and it saturates.
Yeah.
Here, what we see is spurts of growth followed by some decay, and then changes in the rate of growth. Very, very chaotic behavior. It is overall exponential, and it certainly is a dynamo, but it's not why it changes and what's going on, which makes the growth sporadic.
Right.
We wanted to get to the bottom of and to confirm, for instance, that it wasn't something kind of weird or inaccurate or numerical in the model.
Right.
And as a clue as to what was going on, I think if we move to the next plot.
Okay. So that's our volume average magnetic densities, and we are using the pencil code on this one. Very good. Yeah, so I should explain that the pencil code uses non-ideal MHDs. So we have an explicit resistivity, eta, which is in equation 3. Yep, right here.
And an explicit viscosity, which is in equation 2. And these determine the fluid Reynolds number and the magnetic Reynolds number. There are all sorts of other terms which I'll not necessarily go into detail about, but so the higher order terms is eta 6 and nabla 6. These are hyperdiffusion terms which just apply at the grid scale.
Got it.
And don't affect the larger scale structures, which are more determined by the physical parameters.
Gotcha. I'm with you. Go pencil. Okay, very good. So averaging growth rates.
So I might come back to this in a moment, just to comment that this is the table here with a list of this is not all the models, but these are the ones we present in the paper. In particular, we have one high resolution model, which is the half parsec model at the top. Then a number of models with different parameters at 1 parsec resolution, 2 and 4, in order to try and get a sense of how the different physical parameters affect it, and also how well we are reproducing the code in terms of, the physical system in terms of resolution dependence. Okay. I'll come back to a couple of these equations, but I would first like to talk about this image that hopefully is the next image.
That would be figure 2. Okay, let me get on there. A lovely table. Actually know what the symbols mean. I highly recommend that practice, people. Okay, let's go.
But it's this image that I wanted to talk about. If you could just make it slightly smaller, actually, just to begin with, so we can see all 3 images together.
Let me do a global. There we go. So let's do a global first. Okay.
So what these are is a slice from, I think it's well, in fact, it says it's a 2-part. It's a 1 parsec or 2 parsec. It's one of the higher resolution models, I think, actually.
HP2.
I've forgotten my own naming convention now. Oh yeah, high resolution. So this is 1 parsec resolution.
Okay.
And the top panel shows the distribution of the gas density. The second panel shows the distribution of the gas temperature. Okay. And the last panel shows the magnetic energy density. All from the same slice from one particular part of the model while the dynamo was still active. I think it's about 20 mega years, I think, for this model, which is while there was still rapid growth going on in the system. Yes. And one of the things which stuck out to me eventually, once I noticed it, is the unexpected correlation of the magnetic energy growth with the hot diffuse gas. Now, it's quite common when people are doing both observations and when they do modeling to see a correlation between magnetic energy density and density. Partly because the energies are better there's better equilibrium between the kinematics if there's higher density and higher energy and high magnetic field, but also compressive effects tend to push the magnetic field with the gas density. So it's typically and not unexpected that when we look at this region of high warm in the top, that we see that there's a high level of magnetic energy in that top corner. When we look at the cold gas, where I've identified high cold, we also have a region of very high kinetic energy density. What we also expect is we look at the low hot on the left, lower left corner.
Yes.
Lower left, and actually, yes, and lower right, is that the magnetic energy density is low. And that's kind of common to what we'd expect. What was more surprising was in the more middle to the lower right of high hot, is that we have a diffuse medium, very hot, and probably some of the strongest magnetic energy in the whole system.
Oh, wow. Okay.
And this gave us a clue as to what might be explaining these differences in the behavior. So clearly, the fastest, and this was an indication that the growth in the magnetic field is very rapid there, even though there's very little fluid. And it's growing rapidly there, but not in these other two regions. So why is it growing in the hot gas? Is it growing most in the hot gas? And why is it growing there and not in other regions of the hot gas? So this was
good questions. Good questions.
The questions that motivated the rest of the analysis in the work. I think I will go back to this talk about just like the page above or 2 pages above, where we talk about some statistics that were taken.
Yes. Okay.
So it's in this bit. So to understand what we're talking about here, perhaps we can go up to the next page. It might be even a little bit more.
We've got our
right. Okay, so here is a form of the induction equation, equation 6.
Yes.
And actually, if I look at equation 5, very typically when you take an isothermal system and you look at how the dynamo grows, you would see a single line of growth, of exponential growth in the time series. And that would be represented by this gamma, which we've indicated as a gamma bar, to indicate that this is something which is a time average. So it's something, the growth rate is persistent, it's for the whole system, it's a volume average, it's time average, and it applies everywhere. It's
global.
And that depends to a great extent on certain parameters, such as the magnetic Reynolds number. It's much easier, for instance, to grow a dynamo if the magnetic Prandtl number is high. So the Prandtl number being the ratio of the magnetic Prandtl number to the fluid Reynolds number.
Yes.
Sorry, I think I said that. Magnetic Reynolds number divided by the fluid Reynolds number.
Yeah.
And so we would seek to try and understand that, but it's not so straightforward with this system because clearly there isn't a single growth rate. It's not continuous. So to try and understand it better, we wanted to break it down by position. So here is the equation expressed in terms of the magnetic energy density by dotting the induction equation with the magnetic field itself. And this gives us a sense of whether something is growing or decaying. And that varies across the array of the domain. So this function on the right-hand side is not a single value now. It's a field applying to the domain, and it can be positive and negative in different places at different times.
Cool.
Typically speaking, this would be true of any turbulence, but usually with isothermal, more ordered turbulence than the sort we've got with supernova blasts, that turbulence would have a much lower dispersion and there wouldn't be such a big variance in the data. So now if we move down to the equations 7 and 8 and such.
Yes, there we go.
We can sort of approximate this gamma, the small gamma that I showed in equation 5, with this field of gamma, which is a function of position and a function of time, by dividing the right-hand side by the energy density.
It's a relative.
And that gives us exactly the equivalent. If you were to take the log of this, you would now have the log of EB equals gamma T times some function of time.
Yes.
And that we can now break down just by taking the data from the simulation and get a field of values for the growth rate.
Okay, I'm with you.
So that's one way of looking at it, and that's typically how you would evaluate gamma. But it shows the rate of growth, not necessarily the amount of growth. So you could have a position which has an incredibly fast rate of growth, but the magnetic field energy there is very, very low.
And
as a result, therefore, it's growing fast, but it's not actually adding much energy.
There you go. Okay.
So to also understand what's going on from that point of view, in equation 8, rather than dividing by EB as a function of space, we divide by the magnetic energy as an average, a volume average at that particular point in time. So it's normalized in time, but it's not normalized by position. So that then gives us a different indication as to how the growth is occurring everywhere.
Right.
And we can also do similar for the magnetic Reynolds number in equation 9. So rather than having a system, usually people will say the Reynolds number in this model is X.
Right.
And what I'm saying is it's very hard to say what the Reynolds number in this model is. There's such a variation. That if we actually take the equation components themselves, we can compute a field of values as a function of position as well.
Yes, I'm with you.
And then the last point, number 10, is just the fill-in fraction of different components, which could be anything. And in this case, we look at the fill-in fraction for different thermal groups. So we break it into a cold, warm, and hot gas.
Gotcha. Yep. Sounds like an ISM.
Okay. So if we carry on moving down, we'll see what to talk about next.
So there was our table, our data ranges for the sampling. We covered figure 2, Mach number. Here we go. Let's cover some.
Yeah, so I think this is a reasonable place to start. So we really struggled. It took a long time to actually get any pattern or understanding of what was going on. At first, and you can get a hint of it from this figure 3, what we have here is volume PDFs of, in this case, growth rate on the y-axis. And if I can remember this right, is it enthalpy or entropy? I can't remember which one it is, but omega squared on the y-axis. And whilst we have identified in the plots the x, which indicates what the mean value is for these two parameters, you can see from the actual PDF that there's a huge range of variation. There's not really much of a clear indication of the direction of travel, not a great trend within it. And this is one of the better variables to look at in terms of getting some understanding of what's going on. You would see a similar map for whatever variable we tried to look at, whether it's Mach number, whether it was velocity, sound speed, all sorts of things. So we were trying to understand where is the field growing.
Yes.
And you can see it's growing. Some places growing everywhere, other places not growing. This is just where gamma was positive as well. So it's a log plot. So we could only take that part of the domain where it's positive. And of course, there are other parts of the domain where the field is decaying. And that includes in both, these are broken down by phase. So in cold, warm, and hot, they all have phases, which are not phases. They all have locations where they are growing and locations where they're decaying.
Yes.
But there's a net effect at some point. We're trying to understand that.
Okay.
So when we took, if we looked at this data and we took it through the whole time series, it was just a complete mess. It was so much contradictory information. Sometimes you would get a high growth rate with low vorticity. Sometimes you get a high growth rate with high Mach numbers, which seems very unlikely. And then another simulation, and we'd look at all the different simulations, and there was no obvious pattern emerging from what was going on.
Okay.
But what we did was break the time series up into periods when there were rapid growth and less rapid growth, and then split these up into different sections. So what is illustrated now in figure 4 is these data statistics for all the models. So we got these X's that were illustrated in the previous panel. which show the mean values for these arrays
Yes.
for the different phases.
Distribution.
And then we plot them on together for all the simulations and look to see what was happening. Now, in this situation, we were able to actually start seeing some pattern.
Yeah.
So the panels from left to right, in the top row, this is showing gamma, which is normalized by the energy density locally.
Okay.
And the lower one is using this gamma tilde, where we just normalize by the average energy density. That's showing the overall growth rather than just the rate of growth.
Correct.
And the left panel shows the data from each model. It's the third slowest section of growth. The middle panel shows data that is sampled from periods when the growth is in the middle.
Okay.
What's it called? Tertiary. Is it tertiary? I don't know. And then the right one is when we have the periods of most rapid growth. So the first thing that stands out about the top panel is that there's an incredibly strong linear relationship, and that basically can be interpreted as gamma is proportional to vorticity when you take out the square of the entropy. And then the other things we see the clear dependence between growth rate and phase. So the blue indicates cold gas, the green warm gas, and the amber is hot gas.
Great. Okay.
The higher resolution models show the better growth rates because they can get higher levels of vorticity. There's more separation between the phases. We also see that the fill-in fraction, which is indicated by the size of each shape. So the shapes indicate the resolution, but there's the area of the shape is a function of the fill-in fraction. And what we see is that the fill-in fraction increases in the hot gas, we get faster growth rates.
Yes.
So it is true that there are parts of the hot gas where there is not this growth, but in general, it's quite clear that the fastest dynamo is in the hot gas. And the growth is best when the fill-in fraction of the hot gas is highest. So these indicate that there's something good about the hot gas, and we look at that in a little bit more detail in a moment. It's not so clear-cut when you look at gamma tilde. There's contradictory trends. So, for instance, it looks like the cold gas grows faster than the warm gas here. But what that indicates is that we also have the effects of compression. The magnetic field tends to be more aligned with the density, so therefore you've got more magnetic energy in the first place. So although it might not grow relatively as fast, it grows absolutely fast because it's already large. But we do see that particularly when there's rapid growth, that this trend that we observed in the higher resolution models anyway is clear still. So for the green, in the second two panels, the green and the amber models show very, very strong correlation in the same manner.
Fair enough.
What is not so good is in the low resolution. The hot gas doesn't seem to have much growth at all. And I think this is just down to the turbulence doesn't evolve, the very, very small fill-in fraction. It's polluted by mixing with phases. But where we do have them well-resolved hot gas and well-resolved cold gas, then this behavior, particularly in the warm and the hot gas, is still very much convincing that electricity and growth are strongly related. And in particular, we're seeing large magnitude of growth in the hot gas, not just a relative increase in.
Yes. Okay, I'm with you.
So clearly, the hot gas is responsible for the dynamo. So we can move down a little bit.
Okay.
Try and recall what the next plot is.
Mystery one. So figure 4. There is compression ratios, Prandtl numbers, and figure 5 is the summary statistics of gamma.
Yeah, so what we have now is some of the other items that we were looking at, just to show you how they compare with the vorticity.
Okay.
So for the Mach number, there's some contradictory elements there. So as we might expect from models with isothermal experiments, the Mach number isn't good for growth. So as the Mach number grows, which we see moving towards the right,
Correct.
then the growth rates decay. And we see that the Mach number, and it's also sensible that Mach numbers would be lower typically in the hot gas because the sound speed is so much higher in the hot gas that they can sustain much larger velocities. That also is one of the reasons why it turns out they're very good for supporting the dynamo. Because they can have very large flows, very rapid, highly vortical flows, and this is incredibly good for building an efficient dynamo.
Cool.
Something which is kind of contradictory to that is if you look at the individual phases, particularly the warm phase and the cold phase, they actually seem to have within the phase better growth as you increase in Mach number. So if you look between across the phases from cold to hot, then we see the trend we would expect for high Mach numbers, which is that the growth rate gets better as the Mach numbers go down. But within each phase, there seems to be this increase in growth rate, even as you increase Mach numbers. And I think how we can explain that is that although the Mach number is increasing, it's also a sign that the flow is increasing. And as the flow gets more rapid, particularly if you consider that the volume filling fractions and the gas actually has a large range of temperatures. So the warm gas includes temperatures that go from 1,000 Kelvin up to tens of thousands of Kelvin. So within that, you can actually support as you go to higher speeds, a better dynamo, even though this might mean you're approaching higher Mach numbers. And I think that's why we see this kind of counter trend, and also why it was so difficult to actually find this behavior, to understand this behavior, when you look at the statistics as a whole and you don't break it down by phase and you don't break it down by time stamp.
Beautiful.
For the Reynolds number, we would expect the growth rate to improve. So that's kind of the inverse of what's going on with the Mach number, and that's what we would expect. But again, within each phase, there's this counter trend where actually it seems that the lower the RM, the more efficient is the dynamo. And similar sort of explanation is that the what's going on is the RM is getting lower. No, that isn't so straightforward to explain. I did have a good reason why that was, but it's escaped me for the moment.
It'll come back.
It may do. And then in the lower panel, we're showing the fluid Reynolds number behavior. And there's less data there because some of the models we included didn't have any explicit resistivity. So that's the reason why there's no data, because we can't produce. Hang on, that doesn't make sense.
I think it's the other way around.
I think there's a typo in this paper. Be quiet.
Oh no. Okay, let me get my sense here. 4/8 Okay. So now let's go back to this figure. Okay.
No, it's no, I'm forgetting. Yes, we do have a value for the resistivity in every model. It's the viscosity, which is not included in some models. So it's not a typo, that's a relief. So what we see is again, all right, so if you go back to the table.
Go on. Here we go. You do have some zeros in here. Yeah.
Yeah, so in new, there are values where we've just used the numerical viscosity.
Right, yes, correct. I'm with you. Okay. Now that makes sense why there's less in.
So, and we see the same trend that although the data is much more sparse, we still see this kind of countervailing trend within each phase, but across the phases, and as we go to higher and higher Reynolds number, the growth rates increase.
Yes. General trend. Cool.
And I think so RM, just to show how difficult it is to try and track down what the magnetic Reynolds number would be for these models, we see in figure 6 to the right there, how spread out again these are. There's the slightest hint of a trend of dependence. It's almost flat. if you look at about the peak in the lower panel for the
Yeah.
hot gas,
Uh-huh.
there's almost a slightly positive tangent for the line through the peak for dependence between RM and gamma,
Okay.
of gamma and RM, I should say. Whereas at for the cooler phases, it's very much absent. There's not that clear dependence.
Okay.
Although across the phases, if you compare the cold, the warm, and the hot, you'll see that typically growth rates are higher as you go hotter,
Yes.
and RM is higher as you go hotter. And this is also related to the efficiency of the dynamo and the hot gas.
Yeah.
These PDS, I should explain, are for the entire time period. So the multiple data sets, although I think we have broken them up into rapid growing periods, medium growing periods, and slower growing periods, as I described in the earlier plots.
Okay. Good. I am with you. Very cool. Okay. Figure 6. We will go on.
Oh yes, so one of the things that we were interested in was understanding how relevant the different systems were to the type of flow. So we've done a Helmholtz decomposition of the flow in the top 2 panels.
Okay. All right.
So A shows the purely compressive component of the flow, and B shows the purely rotational component of the flow.
Yes.
It turns out that
Compression.
although we use completely compressive forcing, and this isn't a new result, previous authors have encountered the same sort of experiences, that you get the rotational energy is around about 70% of the model.
Okay.
This is particularly the case when you include non-isothermal effects. So because of the baroclinic effect of gradients in density and pressure being non-aligned, this is particularly efficient at form and vorticity. And therefore you get vorticity rapidly created in these supernova-driven turbulence models within the multiphase system, even though you're actually driving all of the flow with explosions, which are purely compressive.
Right. Cool.
We see that it doesn't seem to care a great deal what the type of flow is as to how it affects the growth rates. The growth rates are certainly the scales are the same between the different layers, but I think there's of course there's a correlation between both types of flow. If you've got a flow which is highly rotational and it's sufficient at growing a dynamo, there's going to be a corresponding flow which is not, which is also going to be part of this region which is growing the dynamo. Because the flows themselves will have higher velocities, they'll have similar sort of Mach numbers, and so whilst the magnitude of the vorticity or the rotational flow is significantly higher in general, they seem to have the same trend. But I would argue that what is really going on here is it is the rotational flow which is driving the dynamo, and it's just kind of the potential flow is just taking a piggyback. And then if we look at the lower panel, what this does is it compares the ratio of compressive to rotational flow. So a high value here means that it's highly compressive.
Yes.
Which means that we see that at the very low values, the proportion of the flow which is rotational is very high. And in particularly in the hot gas, especially when it's growing, has very high level of rotational energy.
Yeah.
And this is the key. This is the explanation as to why the dynamo is, because in order to grow a dynamo, you need to wind the magnetic field lines up, and it's the rotation in the flow that produces that. You can get dynamo without such rotation, but this is by far the most more efficient means of doing so.
Fair enough. Cool. Okay. Awesome. Supernova rate, that was in one of the tables. And here we go on.
So here we break down a couple of the models into the different phases. So the top panel here for A, these are all 1 parsec model runs with different resistivity.
Okay.
So they have the same viscosity, and so the only thing that distinguishes them is the resistivity. And the blue line has a resistivity which is a fifth the strength of the red line, and the green line is twice the resistivity of the blue line. So as we would expect, the growth, which we didn't find in some other models, but that was down to changes in when we looked at, we allowed the flow to vary. So we changed the Prandtl number by varying the viscosity, and the result was that we got quite contrary results because the flow was changed. The characteristic of the flow was changed. Sure. Here we kept the characteristics of the flow the same and allowed the characteristics of the magnetic Reynolds number to change instead. So we get very consistent results. So the higher the magnetic Reynolds number, the faster the growth rate, as we see for the blue model. It's not quite proportional to the change in Prandtl number or proportional to the Reynolds number. And what I would argue, although we would really need to go to higher magnetic Reynolds number, which would require us to look at higher resolution in more detail. But the difference between the green line and the blue line suggests that we are approaching, at these low, very low Prandtl numbers, approaching some kind of convergence, which maybe means that it doesn't care so much about the Prandtl number, but that we're still very far away from the physical parameters, and it may just be that we're not resolving sufficiently the difference in the Prandtl number.
Sure. What is the what are the vertical gray dash?
All right. So these are indicating different phases within the model. So between the first 2 vertical lines, you can see there's a period of rapid growth.
Right.
In all models, and they actually are, and they have very. And if you look at the model below, which shows the filling fraction of the hot gas, you see that for all 3 models, that corresponds to a period of increased fractional volume of the hot gas.
Yes. Okay.
We then see a fall in the fraction of the hot gas, and that corresponds to a slowdown for the high Prandtl number models, and actually a decay in growth. Actually, the opposite of growth for the Prandtl number 1 model, which is in red. And then the next period, we see the growth picks back up again as the slightly higher filling fraction. Hot gas, and then it decays again towards the end of that phase, and you can see that it's slower, or it's not growing for the Prandtl number 1.
Okay.
Now, when we get to the last phase, because it's a closed system, and as you keep pumping supernova into the model, you're going to keep heating up the gas. So what we'd find is that inevitably the filling fraction of the hot gas eventually runs away. So we wind up with, in this case, like half the volume is now filled with hot gas. And of course, the growth rate doesn't reflect that for the 2 models that have already saturated, because they've already reached saturation. And so, and therefore, it's not perceptible. You can see there's another peak in the value, but it's not so obvious. But if you look at the Prandtl number model, the 1 Prandtl number model, which is the red line, at this, when the last gray vertical line is there, you can see that this is still very far from equipartition, and then we get another rapid rate of growth. Even though, in fact, that rate of growth is higher than the rates of growth of the high Prandtl number.
The other ones,
And the big difference is less to do with the Prandtl number and more to do with the increased filling fraction of the hot gas and the increased vorticity in the hot gas. So it's not, certainly in these models, they don't seem to be incredibly insensitive to Prandtl number or magnetic Reynolds number.
Very cool. Very nice.
And then the lower bottom, what we've done is for the 2 models, so we've taken the blue and the red models, and we've split those up. So I think the blue line indicates the high Prandtl number model, and the brown line indicates the 1 Prandtl number model, the Prandtl number 1. And then the different triangle colors indicate hot, warm, and cold.
Blow that up. Okay.
And what we see, again, which underlines the importance of the hot gas in this, is in the first range, we have at the very start, the hot gas is tiny.
Yes.
So at around about 10 megayears, you can see that for both models, there's the magnetic energy density, this is the magnetic energy density in these three phases, is very low relative to the other two phases.
Right.
And then when the dynamo takes off and we have that rapid period of growth, we see that that growth is primarily driven by the hot gas in both models, but particularly in the high Prandtl number model.
Right.
And then that continues to be the case, that the growth rate is highest in the hot gas for that model throughout, until eventually it saturates.
Yes.
It's less clear-cut, again, for the low Prandtl number model in this intermediate phase, but when we look at the last phase, when the field really drives towards saturation, again, it's the hot gas where the magnetic energy growth is occurring. So all this points to the fact that the small-scale dynamo in the interstellar medium appears to be something that happens very much in the hot gas.
Yeah, okay.
We look at observations of like molecular clouds, galactic disks, spiral arms. It's always the case that the magnetic field is highly correlated with the high density, with cold gas, with warm gas. The hot gas shows a very little signal. And this, I believe, would be the case. If you look at the later stage after 60 megayears, what you see is that although the saturation of the magnetic field occurred first in the hot gas, it occurs at a much lower level.
Yes.
And as the model proceeds, some of that energy which was there in the hot gas seems to get transferred to the colder phases.
Yes.
So it's entirely consistent with the observations that we see of a saturated magnetic field, because typically these are very fast. It's unlikely we're going to see much evidence of a small-scale dynamo in a lot of our observations, because for most of the existence of a galaxy, this dynamo is going to reach saturation. It will occur, as does happen if you look at individual supernova remnants, depending on the medium. Within that remnant is going to be hot gas, and it'd be interesting to see what the structure of the magnetic field looks like if we can actually measure it inside these remnants. Which that's part of the difficulty. It's difficult to actually get such measurements because of the lack of emissions from such locations.
Fair enough. And then you're probably looking at a Zeeman effect or something. Okay. Cool. Very nice. I got it. I'm with you. Okay.
So I think that's probably the key finds that I wanted to press is how the dynamo depends very much on the phase structure of the ISM.
Yes.
And how active it is in the hot gas. I think, I guess we're kind of running out of time, which is why
we're good. No, we're good. We're good. We're okay. We're okay. All good. You want to cover the cold gas, magnetic densities?
Yes, I think this, trying to remember what we discovered from this. So
there's a reason it's in here.
Yeah, I'm thinking of this figure 9 here. What we see is that the growth of the magnetic field energy in the cold gas is substantially faster than the compression, which is represented by the crosses and squares. So the rate of this is a measure of the dispersion of the gas density, and it's concentrated much more slowly than the gas. So the increase in the magnetic energy in the cold gas isn't down to compression, it's down to dynamo.
Okay.
And, well, sorry, both of these are cold gas. So we see that the magnetic field is growing more rapidly than can be explained by compression.
That makes sense. Okay. And what we got over here, magnetic field densities. You want to cover that?
I'm trying to remember what this one's about now.
If you don't, all good.
Oh, these are just the low resolution runs. So we put them in for completeness, just to show you and see there that we can actually, for a particular setup, get quite a rapid dynamo. I mean, these are over much longer periods of time. To get to saturation, for instance, takes about a gig a year with this model compared to the high resolution runs, which can do within
Oh, got it. Yeah,
10 to
much
50 megayears.
right, much quicker. Yeah, yeah. Okay. Okay, good. And I think the last figure in the article is the magnetic density with sample fits. Okay.
All right, it's comparing the fractional volume to the growth rate. So if we look at the blue dashed line, again, these are low resolution runs.
Low resolution.
There is there is something additionally interesting about this top plot here. So we're looking at a run in which we included stratification. All right, to go back, I now remember what the other plot was about. So we'll have another look at 10.
Want to go back one?
Yeah, if you don't mind.
Yeah, sure.
I think what we're looking at is differences in supernova rate. So the blue cross and the red symbol, I forgot what star, are high supernova rates. By high, I mean the 10 compared to the solar neighborhood rate.
Yeah, yeah. Okay, this is so basically.
And low is, I think, either 1 or 5. In fact, it'll be in the table. But the point is that the higher supernova rate produces increased growth rates, and that's what's shown for the two parsec resolution is the blue crosses, and the lower resolution is the red star. Although that's grown more slowly, it's still growing, whereas the model with the lower supernova rate is decaying with the cyan. I'm not quite sure what those triangular type symbols are called, but that's not even got a dynamo, and that's because it can't generate enough hot gas with the lower supernova rate, because the increased diffusion, and in particular the averaging out of the cooling, because the density structures are more spread out, it loses energy more rapidly than in the high resolution runs, and so it doesn't form the hot phase as well. But with the higher supernova rate, you can get the hot phase, and then you get the growth rates irrespective. Okay. And then comparing this last panel, number 11.
Okay, let's go to that one now. Okay, 0. Interesting one. Interesting choice.
So what's being compared here is two models with the high supernova rate, green and red, which have different Prandtl numbers, and you can see that it doesn't care. So the red and the green don't care a great deal about the Prandtl number.
Nope.
The blue one is with a lower supernova rate, but it is a stratified model. So we didn't have any rotation because we just wanted to look at small scale dynamo. Okay. But instead of having a uniform closed box, this is an open vertical stratified model.
Got it.
In which supernova rate is reduced, but because the gas can escape, the hot gas blows out of the disk, and as a result, there is a much more efficient formation of hot gas. And you can see that the supernova rate is the growth rate is significantly accelerated because we can form much more easily these hot structures. And of course, the stratification helps with the baroclinic effect, because you have much more gradients. Just globally, you've got these gradients as well as locally in the supernova remnants intersections.
So it's almost like a model for a galactic outflow, right?
Yeah. So I mean this is an early indication of what we have moved on to do next, which is to now that we understand a lot more about what's needed to ensure we have a small scale dynamo and what to expect from them. We are going back to the large scale models like this, but now with the rotation and shear, and modeling both the small scale dynamo and the large scale dynamo together. And these, as I was mentioning earlier on, these take much longer.
Yes, years.
We're now invested in evolving the large scale dynamo. So these small scale dynamos can saturate within tens of mega years. We're finding, kind of contrary to our expectation, that the large-scale dynamo takes even longer in the presence of a small-scale dynamo. And one of the models we've just recently submitted for consideration has a growth, takes over 5 gigayears to reach saturation for the large-scale dynamo.
Okay.
We have a high-resolution run, which is the one I was talking about, that takes 2 gigayears. Sorry, it took 2 real years, I mean, to run in physical time. And that has now reached 700 megayears. The small-scale dynamo, in fact, the large-scale dynamo has now reached an equipartition with the kinetic energy density. But it's still growing because the large-scale field actually grows beyond the equipartition. And it's interesting to see that whereas here we need the 1 parsec resolution to get a small-scale dynamo, it does appear that the large-scale dynamo is less sensitive to this, and that we appear to have some kind of convergence in the large-scale structure between the high-resolution run and the lower-resolution run. And that's very encouraging, because they're very expensive to run, and if we can run the low-resolution runs, we can do much more work.
Right. Yes. Very cool. Very cool. And there's this lovely appendix I want to alert people to on the effective Prandtl number, and some interesting plots in a table of that. So do check out that appendix.
Yeah, so that was, we only looked at 3 different Prandtl numbers in this paper. And from the plots, what we show is the spectra for the magnetic field energy and the kinetic energy. And you see that the peak, or the effective number, is not that much different, although for 1, which is the, I think 1 is the, Prandtl number 1 is the pink or peach colored line. You can see that that significantly reduces the effective Prandtl number, the effective resistivity, compared to the other models which reach much lower K. Much lower scales, but higher K. Whereas this is not so much apparent for viscosity.
Fair enough. Okay.
So it is, although I pointed out that it looked like we had something akin to convergence for the Prandtl number 2 and the Prandtl number 5, when you look, you can see that they do seem to have pretty much the same effective Prandtl number.
Yeah. Okay. Cool. Very good. Lovely study. Very lovely. Fred, I want to thank you so much for walking us through your very awesome APJ article. Very nice. And you mentioned it sometimes a little more directly, sometimes a little more tangentially, but I'll push on it a little bit. So where do you think we go with this over, let's say, the next 2 to 5 years? Will there just be one monster simulation that will take 5 years?
We can't. We probably will do a monster simulation. It'll take 5 years, but we can't afford to do monster simulations.
Not many of them. But
and it's not that useful. The main advantage of this high resolution run is just to verify what we can use, the lower resolution runs, and what we can't, and hopefully see if we could. Because we have now. I'm fairly happy that we do get a very good small-scale structure captured by these small-scale dynamos at the higher resolution. And therefore, when we combine that with the large-scale dynamo, we now have something which has a very realistic structure, as you would expect to see in a galaxy, in a disk galaxy. And if we can identify what the differences in the small-scale structures between the high-resolution run and the low-resolution run, either we can at least explain the differences and take that into account, or with best case scenario, we might be able to include some features from what we learn of the high resolution run into the low resolution run. So then when we want to compare them with observables, with what the structures it might be, see how these things affect all sorts of aspects in galaxy dynamics, then we may be able to just inject that. So that would be great.
Correct.
Or at least know what we need to look for. In terms of these small-scale dynamos, one of the weaknesses in this is that we looked at a very low level of parameters, and it would be nice to be able to judge a much larger sweep, and particularly, I think, to get to higher Prandtl numbers, so we can actually ascertain whether we need to go to higher and higher
Yeah.
Prandtl numbers. There is an argument that what matters to the large-scale dynamo in particular in the galaxy is not so much the microphysical resistivity, but it's the turbulent resistivity and the turbulent viscosity. And these are almost certainly much larger in scale and magnitude than these resistive scales. So if we can identify where this occurs, then we can also put an upper bound on how far we need to go in terms of being able to capture the realistic physics of the galactic dynamo.
Cool.
In terms of the large-scale dynamo, we so far again these are very expensive simulations, even at low resolution. And what we need to do is to improve the numerical techniques. In particular, we're working on acceleration of pencil code with GPUs. We've already found a GPU acceleration of at least 10 times over small-scale dynamo turbulence.
Nice.
Now, this is great because if we could increase it by 10 times, we could do that job in a few months rather than a couple of years.
Right. Well, we all know what that happens is you just still got the same 1 year job, right?
yeah, I'm just doing.
But you increase your resolution or whatever it is you're doing, right? So it's always limited by the human. Okay, I can wait a year.
So what we've done with this mixing the small scale and the large scale dynamos, we've now identified the extent to which the small scale dynamo doesn't care about the large scale dynamo. So we've run it in sequence with the large scale dynamo, and with and without the large-scale dynamo, these stratified disks show growth of the small-scale dynamo, which is pretty insensitive. So the small-scale dynamo will work whether or not there's a large-scale dynamo present. What we see is once the field saturates, if there's no large-scale dynamo present, then it sticks around this 2 to 5% of equipartition.
Right.
If you include the large-scale dynamo, it continues to grow. And in fact, what's kind of surprised me is that when you have a large-scale field, which is maybe 6 orders of magnitude below that of the total field, which is dominated by a turbulent field, even at this point when it saturates, it continues to grow, which suggests that the efficiency of tangling of the large-scale field is amazingly high. And that this increased growth after the small-scale dynamo saturated is just tangling of the large-scale field. But it produces tangling of a turbulent field many orders of magnitude larger than the seed field.
Cool.
And now that's at the early stages. Of course, once the mean field grows, then it becomes much more dominant. And we've yet to determine whether this is a numerical effect. Observations suggest that the small-scale structure of the field is significantly stronger in general than the mean field structure, maybe somewhere between 2 and 5 times stronger magnetic energy in the small scales than in the large scales. But ourselves, and I think generally speaking from other people who have modeled in large scale dynamos, the simulation suggests that the mean field is much stronger than the turbulent field. But if we can run this high resolution run to saturation, we get to find out whether or not this is also true as we get more and more realistic small scale turbulence.
Very cool.
And then we'll be able to find out what's true, well, to some extent, whether it's more likely or not that the observations are correct or misinterpret something.
Fair enough. Cool. Very good. Well, I really look forward to seeing this field evolve over the next couple of years as some of these questions get resolved, as we increase our use of GPUs on those codes and all of that. Very cool. Very nice. I really look forward to this. Fred, thank you so much once again.
And thank you, Francis. I've done all the talking. I should enjoy it, but I have enjoyed it. It was very
good. That's the whole point. Very cool.
Thanks very much,
everyone. And I hope this made your astronomy day just a little bit better. And we will see you on the next one. Bye-bye.
Thank you.